was just waiting 140, but it is not coming, so I think we can start. Good afternoon, everyone, and thanks to be following the GGI Tea Breaks seminar series. This is our second pedagogical seminar, and it will be given by Roberto Tateo. The chair is Alessandro Spondrini, and who will now briefly introduce the speaker. Thank you.
This being said, let me just say a few words about the speaker for today, who is Roberto Tateo from the University of Torino. Roberto is a very well-known figure in the quantum field theory integrability community. He has given very important contributions to the study of quantum field theory and especially of integrable models within quantum field theory. In particular, he worked on the computation of spectra for theories in finite volume, so a very interesting and typical problem for the study of integrable quantum field theory. And he formulated a machinery within the formalism of the thermodynamic Bethe answers that allowed people to compute spectra of theories in finite volume, whereas people were, well, originally just constrained to work with the ground state. So that was a very big step forward. Together with Patrick Dory, he did really give a very important contribution there. Another very important contribution, again with Patrick Dory and collaborators, is the so-called ODE-IM correspondence, the correspondence between integrable models and ordinary differential equations, which also has had very profound impact on the on quantum field theory and on the study of integrable models, as well on some important contributions in the context of ADS-CFT and the integrability applied there. But the topic that is most recently being at the center of his work, and also indeed at the center of this talk, is the so-called topic of T-Tbar deformations. And this is something that he and his collaborators have introduced recently, and in parallel, this was also developed by Sasha Zamolodchikov and Fedor Smirnov. And while it is a topic that really starts from the study of integrable theories in two dimensions, it really got to the attention of a large community in theoretical physics, because it turns out to have applications to many, many systems, string theory, quantum gravity, all sorts of interesting problems appear to be related to this very new idea of deformation that goes a little bit in a different direction with respect to the type of deformation that people normally consider in integrable systems and in quantum field theory. I don't want to say anything more about the topic because Roberto will explain to us everything that we need to know. So without further ado, it's my pleasure to give word to Roberto. Please take it away.
Hi, everybody. So thank you, Alessandro, for the nice, maybe undeserved introduction. And so first of all, I would like to thank the organizer of this event for the kind invitation to speak here. So essentially, I'm going to talk about irrelevant perturbation or irrelevant deformation of two-dimensional quantum field theory, and also of the classical interpretation of this deformation. So essentially, T-Tbar, it's a irrelevant operator, and this was defined some years ago by Sasha Zamolodchikov, and is an operator which is irrelevant, is built out of the component of the stress energy tensor. So as already Alessandro mentioned, this is a fairly active, I cannot check, okay. It's a fairly active research field because it's related. So there are connections with string theory, ADS-CFT, and of course with integrability and condensed matter physics. And also people interested in lattice gauge theory is involved in this topic. So it's so you see there are in the last 5 years there are more than 200 papers, most of them with the T-Tbar in the title. Okay, so what what is my main motivation? So the main motivation, let's say general motivation, is the understanding of space of quantum field theories. So from my point of view, the big step was first performed by the introduction of conformal field theory by Belavin, Polyakov, and Zamolodchikov many years ago. So, so the introduction of, so the understanding and the discovery of conformal field theory allow you to understand, let's say, critical phenomena. So for example, we can, using conformal field theory, we can fix and calculate the critical exponent for second order phase transition in condensed matter physics, low dimensional condensed matter physics. We can calculate correlation function. We can 2-point correlation function, 3-point correlation function, so the structure constant. So we can say that we know more or less everything about conformal field theory. And the next step is, so in this, you know, in this space of quantum field theory, I represent this as this yellow dots. Okay, this is a bit misleading because the space of quantum field theory is really infinite dimensional, and also conformal field theory in general are not isolated point. They can depend on a parameter, so have a line or a manifold of conformal field theories. The next step was again taken by the two Zamolodchikov brother, and the idea was that if you know everything about a conformal field theory, let's say this point here, so you know the spectrum, you know the operator content of the theory, you can perturb, so you can move out of this of a conformal point, just perturbing the theory with irrelevant operators. So, and they also discovered, together with many other people, that there were particular directions, so particular operator, which would preserve integrability. So preserve integrability, it means that you can, well, you have somehow some hidden symmetry, you have an infinite number of conserved currents, and a bit like in conformal field theory. And so they discovered that you can break conformal invariance in along certain direction, which would preserve integrability. And usually at the beginning, this type of deformation or perturbation would give you a completely massive theory. So theory with a mass gap. And they being integrable, they could be studied using, for example, the exact S-matrix approach. So if you know the symmetry of the theory, you can impose certain equations, which are called Yang-Baxter equation, together with unitarity and crossing, and calculate completely the S-matrix of the theory. Using the S-matrix of the theory, you can go further and you can study the finite size spectrum through this thermodynamic Bethe-Ansatz method, which was adapted by Alyosha Zamolodchikov to the case of field theory, of relativistic field theories. So in general, in our setup, we replace the renormalization group idea with this thermodynamic Bethe-Ansatz equation, because they depend on the size of your system or volume of your system. You can, if your volume becomes very, very small, then the mass of the particle doesn't matter. And it means that you are describing, you are close to the ultraviolet fixed point. You are going back to the conformal ultraviolet fixed point. So to the initial conformal field theory you are perturbing. But then if you go to larger volume, then you flow into the infrared. And for massive theory, the infrared is essentially trivial. You flow to a trivial theory because the masses, they all decoupled at low energy. So the big hope was instead to find some way to describe a massless flow. So so the interpolation between an ultraviolet fixed point, a conformal field theory describing the high energy region of the model, and then possessing therefore a massless sector that would flow to a non-trivial infrared fixed point. Okay. So this was the second or the third big step, and this was again done by Alyosha Zamolodchikov. So essentially by analytic continuation, he managed to define the S matrix describing the scattering among massless particles. Okay, so these massless particles are interacting particles. So we are outside the conformal point where, for example, right and left mover, they do not interact. In this case, they are interacting non-trivially, and he was able to define the full S matrix, at least for one model or a family of model, and to adapt the thermodynamic beta answers to describe the flow between two conformal fixed points. So the initial example he studied was the flow, which is important, is a flow which is important in statistical mechanics, in condensed matter physics, which is the flow between the tricritical Ising model and the Ising model. So I guess all of you know what is the Ising model. It's a model of a ferromagnet with a spin, quantum spin that might, or spin simply, which can be up and down. And then the tricritical Ising model, in addition, you can omit some spin in the lattice. So you have some vacancy in your lattice. So this is essentially the phase diagram of the tricritical Ising model. And this is the fixed point, so the conformal fixed point. You can perturb in one direction, so so on this first order phase transition line, and you see you have the degeneracy tree of the vacuum. So this is essentially the Landau-Ginzburg type potential. And then this is a first order phase transition, so a line of first order phase transition. But the interesting thing is that or the interesting part of this diagram is this one here. This is a line of second order phase transitions. So can we move along this line? This line is ending at the Ising point, so at the Ising conformal field theory. So as I said, Alyosha Zamolodchikov managed to find the exact S matrix, and he wrote also the thermodynamic Bethe-Ansatz equation, which will give you the exact flow between this point here and this point here, which correspond to the infrared. So once you have exact equation, finite size equation, you can go close to the infrared fixed point and study the neighbor of this point, of this fixed point. And then in this way is discovered the appearance of this T-Tbar composite operator. And the T-Tbar composite operator is defined in this way. So I'm moving here into complex coordinate, and these are the component of the stress energy tensor. So the stress energy tensor at the conformal point is traceless due to conformal and scaling variance. And from this relation here, you can get T-bar and T. Okay. So what he actually discovered was a simple version of the T-Tbar operator, which is simply the product of T, which depend only on the holomorphic variable Z, and T-bar, which is depending only on the anti-holomorphic variable Z bar. This is because at the conformal point, as I already explained or said, that the holomorphic and anti-holomorphic part, they just decouple. Okay, so then you can go further, so you can study further correction close to this point, and you see the emergence of an infinite tower of correction. But after few, let's say, perturbative order, you it's just very complicated, and you lose control of what's going on. So, so what we have at the moment, what we can study with integrable model techniques are a flow. Then from a given ultraviolet fixed point, we can perturb by a relevant operator and then study perturbatively the neighbor of the infrared conformal fixed point. But what about shooting back? So can we start from an infrared fixed point, for example, the aimis model, perturb it and, with an irrelevant operator and reach some point in the UV. So we know that the infrared or irrelevant perturbation, they do not change the infrared behavior of the theory, but they change drastically, or they may change drastically the ultraviolet behavior of the model. So for example, going in this direction usually means that the degree of freedom of your system, they increase, and so it's very complicated. So it's very complicated to tune all the corrections such that you hit in the ultraviolet conformal field theory. So can we, I mean, given that we are in the setup of integrable model, we should be able to say more about this shooting back from the infrared to the ultraviolet. So can we do this, for example, for the T-Bar perturbation, which is the simplest irrelevant perturbation we know? So first of all, we need a definition of the T-Bar operator outside the conformal point. So we know that T-Bar should be built with the component of the stress energy tensor, and outside the critical or the conformal point, the stress energy tensor is no longer traceless. So this it's related to the appearance of this term here, theta, in the definition. So together with the T and T-bar among the component of the stress energy tensor. So if theta is equal 0, then we are at a conformal point. If theta is different from 0, then we are outside the conformal point because the stress energy tensor is not traceless anymore. So this definition of critical T-Bar operator came again from Sasha Zamolodchikov, but only in 2004. And this is the definition. So this T-Bar operator has really some very nice property. So if you are, so this is the definition. So if you are outside the conformal point, then this composite operator, when you send z to z prime, so if the 2 points approach each other, then you develop some singularity. However, the singularity, they cancel out if you subtract this theta square. So theta as z times theta z prime. Okay. So this is not a unique definition because it's up to total derivatives. But if you consider reasonable boundary condition, or for example, periodic boundary condition and expectation value with this boundary condition, then total derivative shouldn't matter. So another way, a simplest way, and maybe more elegant way to think about this T-Bar perturbation or operator is the determinant of the stress energy tensor. So all this expression here can be written up to total derivative as the determinant of the stress energy tensor T mu nu. Okay, so now that we have the definition of this operator of field outside the conformal point, we can think about perturbing a given Lagrangian with the determinant of the stress energy tensor, with this T-Bar operator. So what should we do? It's very simple. So we start from any arbitrary Lagrangian. So for example, 5 to the 4 Lagrangian, or sine Gordon if you prefer an integrable model, and you add it. So you perturb it with the determinant of the stress energy tensor. So with this T-Tbar operator. So you might initially think about tau being very small. However, now that you have a new Lagrangian, you have a new stress energy tensor. So you can calculate the new stress energy tensor, take the determinant of the stress energy tensor and add it again to the Lagrangian. In this way, you have a correction of second order, and you can carry on in this way, building up the total Lagrangian, which will be at finite tau. Okay? So in other words, you are solving this type of equation. So this is the flow equation for the Lagrangian. It means that if you have, if you take the derivative of the Lagrangian with respect to the deforming parameter tau, then this should be equal to the determinant of the stress energy tensor at finite tau. So this is a consistent equation if you put it together with the definition of the stress energy tensor in terms of the Lagrangian itself. So this is the standard Hilbert definition of the stress energy tensor. However, one can show that you can use also other, so for example, the Noether definition of T. And in that case, you would get a different Lagrangian, but you can prove that at quantum level, the result will be the same. And I will go back to this point soon. So if you are working on the Euclidean space-time, then you have a similar equation for the Hamiltonian. So the derivative with respect to tau of the Hamiltonian is again the determinant of the stress energy tensor. Okay, so why is it so interesting? So we have now a way to define or to find the deformed T-Tbar deformed Lagrangian. Let's do it for a simple model. So we start from a collection of n, capital N, free boson Lagrangian, written in this way. You plug this into the flow equation from the Lagrangian, and what you get is this expression here. So you see the emergence of a square root here, which smell a little bit of non-locality, so it doesn't look to be very nice. And then there is this B term, which is, well, essentially an interacting term, is making the field, the independent field, talking to each other. And the amazing things about this result is that this Lagrangian is actually, apart from this constant here, or tau-dependent part here, it's the Lagrangian for the Nambu-Goto theory in the static gauge. So this is the big connection between T-Tbar deformation and string theory, because the Nambu-Goto Lagrangian is the simplest theory, simplest string theory, and therefore the simplest gravity theory. So, okay, now I see that. So this is the general form of the Nambu-Goto action. So it's related again, as I say, to string theory, is the action is proportional to the total area swept by the string in this way, and can be written in this way. So it's the square root of the determinant, and these are the field, the bosonic field. So they depend on x1 and x2 that parameterize that there are an infinite number of ways to parameterize this surface here. So the static gauge is a specific parameterization of this surface. So I can identify one of this bosonic field, x1 and x2 with the coordinate x1 and x2, so let's say space and time, and then I can rescale the remaining d-2 field, which correspond to the orthogonal fluctuation of this surface in terms of this bosonic field phi, as before. Then if I do this gauge fixing and this redefinition of the field, then this expression here, so the expression for the Lagrangian density, becomes the Nambu-Goto Lagrangian in the static gauge. So the one I obtain using the T-Bar perturbation. So this is again the big connection with the string theory. So we can do more because we have a flow equation for the Lagrangian. So we can start from an arbitrary Lagrangian. So for example, I can start from a Lagrangian with an arbitrary potential V. So let's say L of V is equal to the kinetic part, so this part here, plus the potential or minus the potential. Then I can plug the initial solution. It's a first order differential equation in tau, is nonlinear, so it's quite complicated to solve in general. But if I plug this initial condition here and I look for the solution, this is what I find. So the form is again very similar to the Nambu-Goto Lagrangian. So especially this part looks pretty much the same. So there is the B term is identical to the previous one. So the one for the Nambu-Goto Lagrangian. This L0 is only the kinetic part, and this tau bar is correspond to a redefinition of the tau of the perturbing parameter. So it's a local redefinition depending on the potential V. And then there is this additional term, and then when you send tau to 0, this ends up to be this term here. So the potential term in the Lagrangian. Okay, so this, in this way, you really can perturb any theory you want with this T-Bar operator or T-Bar field, because we are at the moment we are only discussing the classical interpretation of this T-Bar field. So, for example, we can study an integrable model. The typical example of integrable quantum or integral field theory is the Sine-Gordon model. So the form Lagrangian, the T-Bar deformed Lagrangian has this form. So the complication is related to this square root here, which contained this redefined perturbing parameter and the kinetic part of the Lagrangian. And we know that the Sine-Gordon model is an integrable theory and that T-Bar is not spoiling integrability. So we can study what's going on. So what happened, what kind of deformation correspond to this T-Bar operator. So the potential, as you all probably know, it's a periodic potential of Koch type. And this potential for the Sine-Gordon model lead to different type of excitation. So you can have a kink excitation. So for example, if your field is interpolating between this value here, this vacuum here, to this here at plus at x plus infinity, so from x minus infinity to x plus infinity, if the field is interpolating between this vacuum and this one, then you have a kink solution, which has this form. Vice versa, you can interpolate from this vacuum to this one, and you have an anti-kink solution. So these are the so-called kink solution, and they are essentially solitons. Then in addition to kink solution, you can have fluctuation of the field around one of the minima, and these are usually called a breather solution. So one thing we wanted to understand is how T-Tbar is deforming, which way is deforming the solution. So the soliton solution, the kink solution, and maybe the multi-kink solutions. So they started from this Lagrangian, the equation of motion are this one, and they look quite complicated. So for a few months, we really tried to solve this complicated equation of motion. I mean, the complication is coming from the fact that you have this square root here at the denominator, and also here.
Roberto,
so we tried different.
I think that there is a question from your colleagues, so I will unmute them. Let's see.
Okay, Roberto, just a very simple question. Is there an intuitive reason why here, under the square root in S, you don't get the quartic part in the derivatives?
Okay, yes, because they are not, you know, you solve this equation, the Lagrangian flow equation, and you don't introduce any extra derivative. So at quantum level, maybe if you want to treat this at quantum level, then you might be forced to replace some higher power of this object here with a higher derivative. But it's not introduced automatically by this process.
Okay, it's just a different solution.
Yes.
Okay.
Okay.
Maybe if there are any other questions, since we have a little break, or since there was one question. But if not, we just continue with the talk. Thanks.
Okay, so so this is really the answer. So this Lagrangian is the answer. So it's the solution of the flow equation together with the definition of the stress energy tensor in terms of the Lagrangian. So this equation are really quite complicated. We try to solve this equation perturbatively, and after a little bit of work, we managed to find the form kink solution. And full stop. So we try to apply the whole machinery of integrability. So one thing we were interested is the map between soliton solution and pseudospherical solitonic surface. So these are called solitonic surfaces. Actually, it's old stuff. It's related to differential geometry of 200 years ago or something like that. And actually, it was through the study of pseudospherical solitonic surface that the Sine-Grodor model was initially introduced. So what we wanted to understand was the kind of deformation would give this T-Tbar to the pseudospherical solitonic surface. And to our surprise, so we did all the calculation. It's again, should say it's differential geometry. It's related to some object called Lax operator that exist in integrable models. So we calculated the deformation of this surface, and we understood that it was actually zero. So there was no deformation of the solitonic surface at all. So this is the no deformation. It means that essentially the T-Tbar should be a change of variable. So it's again just a simple, should be interpretable as a simple reparametrization of the surface. Which would not affect the shape of the surface itself. Okay, so and for this, in following this way of reasoning, we end up with a transformation, a field-dependent transformation, which allow you to describe the T-Tbar deformation. So what I mean is the following. So this is a Jacobian transformation between the original variable, which I denote with Z and Z bar, and some deform coordinate system, which I call W and W bar. And the Jacobian, so the relation between the deform W and W bar and the undeformed Z and Z bar, is described by this Jacobian transformation. So it's a field-dependent transformation. And the net result is therefore that if you are looking for a solution of the deformed equation of motion, let's say phi of tau and Z, this is given by the undeformed solution, so phi 0 at tau equals 0, on the deformed coordinate W of Z. So it's a sort of geometrical interpretation, is a sort of gravity between inverse comma, because it's really just a change of coordinate, but a field-dependent change of coordinate. So if this is true, then it must be true that if you start from the form equation of motion, you apply this change of coordinate, then the form equation of motion should reduce to the original unperturbed one, but on the deform variable, on the deformed coordinate. And this is true. So you use this Jacobian in this equation, and then it's automatically mapped into the undeformed equation of motion. So this is the classical interpretation of T-Tbar. It corresponds to a field-dependent change of coordinate. Not moving. Okay, now, okay, at this point we were able to find the kink solution, not only the kink solution, but other solution like the soliton or like the breeder solution, etc., etc. So this is what happened for the kink solution. So this is the solution interpolating between one vacuum at x minus infinity to another vacuum at x equal plus infinity. So this is the standard soliton. This is or kink. This is at tau equals 0. Now, if we switch on tau and made it negative, then the kink solution is still interpolating because the symmetry of the potential of the original potential is maintained, but it's now the solution is becoming flatter and flatter in this way. Now, for the other sign, the opposite sign of tau, then you see that the shape of the kink is now bending toward the left and become multi-valued. So it's essentially developing what we usually call shock wave. So at this stage, the interpretation of field theory is lost, but the interpretation as field theory as a surface is still maintained. Okay, so the same happened for the breeder solution. So the breeder solution is an oscillation about the one of the vacuum. And this is time, so the breeder is really breeding, so it's oscillating in time in this way. And this is the undeformed solution. Then now you increase tau above 0, and you see this blob here is shrinking in this way, and it again become multi-valued. So this happened after a certain critical value of tau, but you know, the interpretation as a surface is still maintained. So this, even for theory with the non-zero potential, then you have a string-like interpretation. For tau negative, the blob is becoming larger and larger, and at a certain point, this blob would intersect with this other blob, and again, it becomes multi-valued at a certain critical value of tau. Okay, so I should stress again that this T-Tbar deformation is related to a dynamical change of variable, so solution that dependent change of variable, and is defined through this Jacobian transformation. Now, in the Saint-Gordon model here, you have the potential on the diagonal and the potential there, and this is essentially part of the kinetic term, which is T-bar, and this is T. So the general transformation for an arbitrary theory, not only for the Saint-Gordon, so an arbitrary theory, even if it's not integrable, is the following. So you have to replace V with this is proportional to the trace of the stress angle tensor and put T-bar and T here on the Jacobian. So what's the secret in this Jacobian transformation? So the secret is that if you impose the equality between mixed derivative, so second order derivative, so for example, this should be equal to this. If you impose this, then automatically the stress energy tensor, so the component of this Jacobian, should give you a conservation law. Okay. So this is why the Jacobian has this form, because it has to impose in this consistency relation, it should give this conservation, a conservation law. And this also tells you that there are an infinite number of ways to deform this type of map, especially if you have a high order of higher spin or higher Lorentz spin conserved currents. So you can replace in this Jacobian transformation some other conserved current. And this led already to many other T-Tbar type deformation. The other interesting fact is that if you perform this change of variable into the action, so at this level, you start from the Lagrangian at finite tau. You perform this change of variable in here, and what you get in the W variable is that the original Lagrangian L0 of W plus tau T-Tbar, but the unperturbed one. So essentially, if you perform this change of variable inside the action, it's undressing almost completely the Lagrangian, apart keeping the first order perturbative term in the T-Tbar.
May I ask a question?
Yes.
So you said that you can write there in place of T and theta and T-bar higher spin currents, but you could also write lower spin currents, like just U1 currents, if you had
yes.
currents here.
Yeah.
And
yeah,
that would give you the usual JJ bar, for instance.
Yes. Okay, in that case, you have a model of this family of T-Tbar, which has also been studied.
I was thinking even simpler of marginal deformations of CFTs, for instance, like JJ bar. Could you also understand those like that?
Yeah, I think you can, you know, the important factor in this map is that you respect, so this equality is fulfilled. Okay, and yeah, any other, so if you replace the T mu nu with other currents, as far as this equality is respected, then you have a new perturbation, so new irrelevant perturbation of your theory. Okay, so why this point is important? It's important because now you can work from this way, from here to this. So since this is this change of variable is universal in some way, and you can define it for an arbitrary theory, you can start from this here, which is the Baire Lagrangian plus the Baire T-Tbar, do the inverse of this transformation and find the perturbed Lagrangian. So this is a very efficient way, and you can apply this this trick to get the deformed Lagrangian for even for non-relativistic invariant theory. Okay, so let's move to the quantum theory, which is even more interesting. So first of all, I should underline that I'm not, at this stage, I'm not quantizing the classical theory, in the sense that we first obtain the quantum result using the quantum S matrix, the full quantum S matrix, and then we move to the classical. So we did the classical limit to understand what was the meaning of this deformation at classical level. So this is what I'm saying here is not a quantization, but actually should be read on the other direction. So we first obtain the flow equation for the quantum spectrum and then interpreted it at the classical level. So we have full control of the quantum theory in this case. So the quantum equation are obtained starting from the flow equation for the classical Hamiltonian and taking expectation value over a given state n. Okay. So this is essentially the energy En of the state. This part here, so you take the expectation value of the determinant of T mu nu, so T-Tbar, and they use this important result by Zamolodchikov, which is related to a factorization property of the T-Tbar operator. So this is the claim. So the expectation value of the determinant of T mu nu is equal to the expectation value of the single component of the stress energy tensor. So this essentially was proved by Zamolodchikov in the paper in the 2004 paper. So this is the important property, and is due to, again, to the conservation law associated to the T-Bar perturbation. Okay, now when you do this, after you do this replacement, you can associate to expectation value of the single component of the stress energy tensor. For example, for T22, you associate it to the energy. T11 is associated to the pressure, so it's the derivative of the energy with respect to the volume R, which I should say is a circumference with periodic boundary condition. And T12, the component, the off-diagonal component, are related to the total momentum of the state. So Pn, which is quantized in the standard way because the T-Bar perturbation has spin 0, so is not spoiling this property. Okay, so you put all this information together and this is what you get. So it's here on the left-hand side, you have the derivative of the energy level with respect to tau, the perturbing parameter. On the right-hand side, you have the derivative of the energy with respect to R. And this is, this tells you something, again, that there is a geometrical interpretation of tau. So you change tau and somehow you change R, the volume of your system. And then you have this extra term that it's a source term. So this equation, it's it's actually very, very well known in hydrodynamics. It's called Inviside-Burger equation. But this is not classical hydrodynamic because we are evolving the quantum spectrum of the theory. So why this is so, this is interesting. Okay, it's a powerful tool. It's a first order equation in tau. So you give the initial condition of the spectrum at arbitrary R. You use this equation and you find the quantum spectrum at arbitrary value of tau. The other important fact is that this coefficient here is playing essentially the role of velocity. Okay, so the velocity is proportional to the energy. So it means, for example, for hydrodynamic, it means that you start from wave of this form, let's say Gauss form, and you evolve in time, then it's developing again a branching of the solution in this way. So wave breaking in hydrodynamic. But again, we are now talking about a quantum spectrum, so we would like to understand what's the meaning of this wave breaking at the level of the quantum spectrum. Another important factor is that if, for example, you set the Pn equals 0, then the simple solution for the energy is the following one. It's similar to the, the trick we use to find the deformed soliton equation. So the energy En at R and tau is equal to the undeformed energy, because tau here is 0, but with a redefinition of the radius of the circumference R in terms of the energy itself. Okay, so this is the standard solution of the Berger equation without a source there. Okay, so so the Gauss shape is certainly not the shape of the quantum energy spectrum of a model. The quantum energy spectrum of a model at finite volume looks more like this. So for example, this is the finite size spectrum for the massive Majorana fermion, which correspond to a perturbation of the Ising model, conformal field theory. So this is the vacuum state. So a small r is blowing up toward minus infinity, and then at large r, large volume is normalized such that they go exponentially to 0. Okay. Then you see above this vacuum state, there is the gap. So this is a massive theory. So this gap here is twice the mass of a fermion. And then you have the continuum above this, twice the mass gap. Okay. But what is important in this picture is that at r equals 0, so r equals 0, it corresponds to the ultraviolet limit, all the states, they blow up either to minus infinity or to plus infinity for the excited state. So at r equals 0, the behavior is the typical behavior of a conformal field theory, which is characterized by a coefficient related to the Casimir coefficient of a conformal field theory, the effective central charge, divided by r. So it develops a pole singularity at r equals 0. Okay. Have problem changing the slide. Okay, so this what's happened if you turn off the parameter tau. So this dashed line corresponds to the original vacuum state. So it's going up to minus infinity for small r. And now if you increase tau a little bit, then you see that this line here, which was vertical here, was a pole singularity, is now bending toward the right, and is the solution become multivalued. So you have a shockwave phenomena, but at the level of the energy spectrum. So this is a square root type singularity, and it is connected with another square root singularity here in the unphysical region, because r is smaller than 0 in this part here. Now let's have a look. Let's see what's happened for the excited state. So the excited state, at least the higher one, have effective central charge, which is now negative, and the opposite phenomena happen. So now this energy level, which was originally blowing up at infinity, is now bending toward the physical region, which correspond to negative R, while a physical state coming from the negative R region is now moving and appearing in the physical region corresponding to positive volume. And again, the net result is doubling of the energy level in this way. Okay, so now, so this is a general phenomena. If you have a conformal field theory originally at describing the ultraviolet limit, so therefore at R equals 0, then you see the appearance of this tachyonic-like singularity, which was already well known in string theory. And indeed, if you start from the conformal spectrum, you solve the Berger equation starting with the simplest 1 over R initial condition, then you end up with this expression here. So this E plus here corresponds to the total energy of the right mover sector, and this is the total energy of the left mover sector, and you sum them together to get the total energy of the theory. This is what you get. So this is again the form of the exact form in the case of conformal field theory, which is matching the string result in the critical dimension, which is D equal 26, correspond to effective to C here equal to 24. And this is the precisely for D equal 26 and C equal 24 is the Nambu-Goto spectrum. But this is more general because you get this result for an arbitrary conformal field theory. Okay, the last things I want to mention that, you know, you see, you have a square root here. So when this, the quantity under the square root becomes 0, you reach, you have this tachyonic singularity, and this corresponds to a critical radius, which is the square root of 2 pi c tau over 3, in the case in which p is 0. Now, a way to interpret this tachyonic singularity is to consider your system on a torus, where you interpret as the direction R as 1 over the temperature, and the direction L, this one here. And for simplicity, we can consider a C equal 1 alpha, which is the Ising model, and send L to infinity. And then you discover that the level degeneracy, so the number of states at fixed n, is actually growing exponentially with the energy, where the energy depends on the quantum number n in this way. And this exponentially growing of the degeneracy is related to the presence of a maximal temperature, which is called the Hagedorn, usually called as Hagedorn temperature. So you just have to use the definition of the entropy in terms of the energy and the temperature, which give you this definition of T in terms of the entropy. And then you can, using this expression, you immediately find that there is an upper limit of the temperature, which exactly corresponds to the critical radius we identified before in the expression for the energy. So this is more or less what I wanted to say, and thank you very much for your attention.
Is there any connection with the Liouville theory? I mean, if you are moving away from critical string, you enter the regime where you need the Liouville theory for describing the theory. So the question is there any connection with the Liouville theory? Because nobody has a really completely hand on Liouville theory.
Okay, yeah, I think it's totally unexplored. So of course I can, T-Bar perturb Liouville field theory, but it's not the same. That is not really answer your question. I think it's totally unexplored. At the moment, I think the only relation with gravity is with JT gravity. So yeah, I would say no. I don't know. I mean, from our point of view, there is no way of seeing the emergence of the UV field.
I think there is maybe one relation, but it's not so clear to me, and it's a bit on a convoluted way. In the context of ADS3 CFT2, there are some cases in which the CFT2 has a Liouville description, and it is known that basically T-Bar appears in a very natural way in ADS3 CFT2, but it's perhaps not a very direct link. So yeah, I'm not sure if that's what Igor had in mind. I think we can move on with further questions. Let's see. Yeah, I think you're unmuted.
Am I the next question?
Yeah. So sorry. Yeah.
Can you show the video? So because you have to enable my video.
Yeah. Can I?
Okay.
No, I think I will have to ask the GGI staff to make you a co-host.
Forget it, and I'm sorry. I would like
try to do it.
I unfortunately cannot do it myself, but
okay.
Maybe you can start. You can start asking a question, and then we'll.
Okay.
See.
So first, I want to thank you for a very nice talk. Thank you very much. And second, you mentioned motivations, but I think one motivation which physicists have, they try to do a crime and escape the punishment. So here one is trying to escape the Wilsonian picture. One is adding, as you said, the T-Bar operator. And the question is, in the quantum theory, will we be punished? Now, I think that there is an indication that one is punished. If you take the two-dimensional CFT in the range of parameters where everything is okay, no tachyon,
yes,
everything is okay. And then I think with Barbon, Jose Barbon, we have shown that if for any two-dimensional CFT, if you add the T-Bar deformation, there will always be an energy above which the specific heat will become negative. So the issue is not only that you begin to get like a Hagedorn temperature, but the question is how exactly do you approach it? And if you approach it from above instead of from below, you get a negative specific heat. So for any two-dimensional CFT, no matter if it's compact or not compact, you get the same answer that there is always an energy above which the specific heat becomes negative. Okay. And the theory with the specific heat becoming negative has problems in correlation functions. When you calculate the 2-point functions, they diverge, you need to put cutoffs and so on. So I just want to point out that there seems to be a punishment. It's not that one escaped without any punishment.
Yeah, so
let me just cut in to say that now you can actually share if you need to open your video or share. That should work now. Sorry to interrupt.
So I think the problem is that I think it must be related to the fact that you lose locality. Okay, so I think it's the same problem. I mean, the problem of definition of correlation functions must be related to the fact that you lose locality.
I'm not sure. You can leave. I think you can lose locality without having negative specific heats. I'm not sure the two are tied. I mean, these could be two different features, not necessarily the same.
Okay. Thank you.
Okay, that was my comment, and thank you again for Roberto.
Thank you very much. Any further questions? Maybe I will ask one myself. So one of the motivations was to go against the RG flow.
Yes.
Is it possible to see that the C function increases in this, I mean, the C function that is normally used to define really the idea of degrees of freedom decreasing along the RG flow?
Okay. Yeah, I think for one sign, so let's say usually called good sign, where you don't have, you know, tachyons, then for the good sign, then you see an initial increasing of the C function, while for the other sign, a decrease. So usually when so what we were getting at the time, and so many years ago when we were studying this massless flow using thermodynamic Bethe ansatz, the T-Tbar was always coming with the same sign, so this positive sign. So where excitation go are not superluminal.
I think there is another question by PMA. I'm not sure who that is, but they can unmute now.
Thank you. Yes, this is Paolo Aschieri speaking. Ciao Roberto, ciao Alessandro. Well, I just wanted to have a curiosity. You said you spoke about the possibility of these solutions that develop multi-valued, that become multi-valued. Now, usually one way, apart from saying that the surface is anyhow the solution, is to really develop a shock wave in the sense of a Rankine-Hugoniot condition. And I was wondering if there is an analog here.
So, okay, you are talking about the classical.
Yes.
Sure.
Yes.
Well, I don't know. I think from my point of view, we also studied, for example, non-relativistic case like the nonlinear Schrödinger equation, which is related to the dynamics of vortex filament there. And in that case, I think it's naturally comes out that the true picture is really as a filament and not as a soliton. So you really see that this soliton winding up and becoming multi-valued, but you can unwind it if you look at the full picture in the higher dimensional space. I think even for non-relativistic case, you see that the string picture seems to be the right one.